Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll study K-means clustering algorithm. In this course, so far we studied supervised machine learning algorithms where training data consists of features and labels. There is another class of machine learning models where training data contains only features and labels are not available. They are called unsupervised machine learning algorithms. Clustering is an example of unsupervised machine learning algorithm. And clustering is the process of grouping similar data points or examples in the training set in the same cluster. You may wonder, what do we do with training examples represented only with features but without any labels? Well, there are several applications of clustering, and clustering is widely used in many applications such as customer profiling, anomaly detection, image segmentation, image compression, geostatistics, and astronomy. Let's look at components of clustering. Just like any other machine learning algorithm, clustering also has 5 components: training data, model, loss function, optimization procedure, and model selection and evaluation components. The training data consists of examples with only features, and note that the labels are not available. So training data D only has examples represented with features, and there are n examples, and each example is represented with m features. Let's look at the model of clustering. So we have examples on the rows and clusters on the column. And the model of clustering is to assign an example to a cluster. Now this membership could be hard membership where the point is assigned to exactly one cluster. So it has got 1 only for one of the k clusters and rest other entries are 0. So this form of clustering is called as hard clustering. There is another form which is called soft clustering, where instead of having 1 or zeros, we have probability of membership of a point to a particular cluster. And the sum of all the memberships to the k cluster for a particular point sums up to 1. So this is called as soft clustering. In this course, we will be focusing more on hard clustering. So K-means clustering algorithm is an example of a hard clustering algorithm. So let's see how cluster is represented. So cluster CR, where R is between 1 and k, is represented by centroid, and the centroid is calculated as an average of vector of points in that clusters. So mu R is the centroid of rth cluster. It is calculated as the average. These are the xi belongs to R. So basically this is the cardinality of the set or the points that belong to cluster R. So we are using that for taking the average, and here we are summing up over all n points the n vectors and examples, and only those examples are added that are part of this cluster. So that is ensured by this particular function 1 of xi belongs to R. So only those xi's that are in cluster R will return 1 for this particular expression. So in this model there are two unknowns. We do not know cluster centroids and we do not know membership of points to the clusters. So we only have points, but we do not know exactly which cluster each point belongs to, and we also do not know about the cluster centroids. The data points are usually assigned to the nearest clusters based on a chosen distance measure. Euclidean distance is one of the commonly used measures in this process. The Euclidean distance between a data point xi and cluster center mu r for rth cluster in n-dimensional space is calculated as follows. So this is the formula for calculating the distance between point xi and the cluster centroid mu r for rth cluster. So we simply sum up the square of the difference on each of the m dimensions between the point and the centroid, and we take square root of this particular inner summation, and that becomes the distance between the point and the cluster centroid. So we define the loss function in form of what is called as sum of squared errors. So we sum for all k clusters. For each cluster we find what is the error, and the error is basically the square of distance between the points in that cluster and the centroid of that cluster. So that is basically the error for every cluster, and we sum of these errors across k different clusters. So you can see this particular situation. This is the centroid for cluster 2, and these are the points in cluster 2. This is the centroid for cluster 1, and these are the points in cluster 1. So the error for cluster 1 will be the square of the difference between each point and the centroid, and we sum it across all the points in this particular cluster. And in the similar way, we can find out error for this particular cluster. We sum up these two errors, and that is the error due to the clusters that we have selected, or cluster centroids that we have selected. We use k-means clustering algorithm for optimization over here. We start off with k initial cluster centers, and these cluster centers are randomly initialized. Then what we do is we assign each point to the closest cluster centers. Then for each cluster, we recompute its center as the average of all its assigned points. We repeat the step number 2 and 3 until centroids do not move or certain number of iterations have been performed. So it's a simple algorithm with these 4 steps. And k-means algorithm is an instance of a more general algorithm called as expectation maximization, or EM. So let's look at an example of k-means clustering algorithm. So here we generate points from 3 clusters using a sklearn library. So these are artificially generated data points such that they form roughly 3 clusters. Then these are the centroids, and these are the clusters that were formed after running the k-means clustering algorithm. Let's look at some of the limitations of k-means clustering algorithm. One of the limitation is local optima. K-means does not reach optimal sum of squared error all the time because it is sensitive to random initialization. And if the initialization is not great, the algorithm could reach poor clustering solution. There are 3 clusters, but these 3 clusters are formed such that these 2 clusters are merged, and this cluster is broken down into 2 different clusters, which is not a great solution. So k-means does not reach optimal SSE because of poor initialization. Another problem with k-means is if data is not in a spherical shape, then k-means clustering algorithm will return suboptimal clusters. So here you can see that there are 2 clusters which are in the shape of moon, and because of this specific shape, what has happened is some part of this particular moon has merged with the other moon and vice versa. And we can see that this is not really a great solution. So if the data is not in a spherical shape, k-means clustering algorithm can suffer. For large data sets with large number of data points and features, k-means algorithm will be quite slow to converge, and you know the reason for that, because k-means clustering algorithm calculates pairwise distance between the points and the cluster centers. Another problem is that k is not known at the beginning. So it is computationally intensive to compute k by elbow method, which we will see shortly, because it involves running the complete algorithms for many possible values of k. So typically, since k is not known, what we do is we basically try different values of k, and each value of k can take quite a long time to run. So finally, we evaluate clustering solution by SSE measure, and SSE measure was defined as a loss function. So let's look at how do we find suitable values of k. There are two methods. One is elbow method that we mentioned a couple of slides before, and second is Silhoutte method. In elbow method, what we do is we basically try with different values of k, and for each value of k we calculate the sum of squared error. And you can see that if we try with small number of k, or the value of k that is very small, let's say k equal to 1, we have produced the maximum error. And then once we increase the value of k, the error reduces, and error reduces to a point, and beyond that the error is not reducing that significantly. So there is what is called as an elbow point, and that elbow point generally denotes the optimal number of clusters. But in order to perform this model selection, we have to perform multiple runs of k-means, and for each of the run we have to record SSE and then plot this particular graph to find the elbow point. The second method is to Silhoutte, and we calculate the Silhoutte coefficient for each cluster, where A is the mean distance between the instances in the cluster and B is the mean distance between the instance and the instances in the next closest cluster. So Silhoutte coefficient is calculated as the ratio of AB and max A comma B. And again, here we try with different values of k and calculate the Silhoutte coefficient for that. And you can see that the point where the Silhoutte coefficient is maximum is selected as the optimal number of clusters. So here the Silhoutte coefficient is maximum for k equal to 3. So k equal to 3 is an optimal number of clusters in this particular case. Here there are a couple of examples that we are showing where we have applied k-means clustering algorithm. So this is an example of image segmentation where we have to segment different aspects of images. So you can see that one of the possible segmentation is we have bird as one segment, and the support that it is taking and the background is another segment. So this is an example of image segmentation generated with k-means clustering algorithm. We have used MNIST digit dataset for classification demonstration quite extensively in this course. Now we use the same dataset for demonstrating the k-means clustering algorithm. Here what we do is we only supply the images to the algorithm and we withheld the label. The labels are not shown to the clustering algorithm. After performing clustering, we calculated the confusion matrix based on the digits that are forming different clusters. And you can see that we have gotten a pretty decent confusion matrix compared to different confusion matrix that we have seen in our course. And there are standard issues like confusion between label 5 and label 9, or label 8 and label 9. This particular confusion is a bit surprising where label 1 is getting confused with label 8. So this is surprising. We have not seen this in our other demonstrations. So in this video we studied k-means clustering algorithm, and k-means clustering algorithm is an instance of a hard clustering algorithm.